What happens when you have a chain rule inside of a chain rule? Or one function inside of another function inside of another function? The rules still stay the same. In other words, what was our rule for our chain rule? Derivative of the outside function, keep the inside the same, then do the derivative of the inside function. So first of all, I'm going to rewrite that squared with brackets. The 2x minus 1 is inside sine, but the sine 2x minus 1 is inside the square. So my most outside function is the square. Chain rule says, do the derivative of your outside function, keep the inside the same, then do the derivative of the inside. So if I start with the derivative of the outside, my 2 would come out in front. I keep the inside the same. Then I need to multiply by the derivative of the inside. But the derivative of the inside is another chain rule. And in that next chain rule, now what's my outside function? The sine. What's the derivative of sine? Cos. So I do the derivative of the outside, which is derivative of sine is cos. I keep that inside the same. And then I need to multiply by the derivative of that inside, which is 2. So we have a chain rule with a chain rule inside. But you just keep following the words. Every time you get a derivative, you're like, what do I do in this case? And you follow your shortcut for that. And if you run into another rule in that shortcut, you follow that rule. Of course, you could simplify this if you wanted to, but you could leave it with the color coding as well. So again, what we have to recognize is what is our outside function, what is our inside function. And if you have something inside of that, you're going to have to do your chain rule a second time. So again, if I see that tan to the 4, I might write an extra set of brackets to put that as the power of 4. What is my most outside function? The power of 4. So first, how do I do the derivative of a power of 4? I bring the 4 out in front. I keep the inside the same. Subtract 1 from the exponent. Now I have to do the derivative of the inside. What was my inside? Tan 2x. It's another chain rule because now there's a 2x inside of the tan. So now what's my outside function? Right, my outside function is tan, and its derivative would be secant squared. So we get secant squared, keep the inside the same. And then we have to multiply by the derivative of the inside, which is 2. And of course, you could simplify that. I'm not even going to put the simplified up. You could multiply the 2 by times the 4. No problem. So it is a matter of recognizing what's your outside functions, what's your inside functions, what's your most outside function. Okay, I could do a quotient rule here. But anytime there's just a number on the top, it makes sense to move things to the top so you don't have to do a quotient rule. And here, I decided to put the brackets and the minus 5 on the outside so you can see that that minus 5 is your outside function. And inside of it, you have a sine 6x. And inside the sine, you have a 6x. So we do have a double chain rule here. Most outside function, the minus 5. So the minus 5 comes out in front, subtract 1 from the exponent. Then we do the derivative of the inside, which is the sine 6x. And it is a chain rule, because there's a 6x inside of the sum. Okay? How do you know when you have a chain rule? When whatever is inside the function has its own derivative. If you just have an x inside, I guess technically you could do a chain rule and you'd have to multiply by 1 at the end, but it would be sort of not important to do. So now, my inside function was sine 6x. I'm going to do that derivative of sine is cos, keep the inside the same, multiplied by the derivative of the inside. So with these shortcuts, most derivatives are one-liners. You do all the work in one line, you're done. You either know the shortcuts and get full marks, or you don't know the shortcuts and you're in trouble. Preliminaries. I see a square root. I'm going to change that to a half. I find the exponent one sometimes the hardest to see. What's inside of what? What is the most outside function here? The half exponent is not the most outside. 4e to x, to something. The e to the something, this whole part, I'm going to put it in a green box. This whole part is in the place where an x normally is with e to the x. So that green box is inside of an e to the x. And then the x squared minus 4 is inside the exponent of a half. So my most outside function is the e to the x. How do you do the derivative of e to the x? E to the x. So you keep everything exactly the same. Now I have to do the derivative of the inside function, which is a chain rule again, because I have an x squared minus 4 inside of a power of a half. So I do the power of a half first. Half comes out in front. Subtract 1 from the exponent. And then finally, I can do the derivative of the inside, which is a 2x. Those 2's could cancel out. We could simplify this, but this is fine. Okay, try the bottom one on your own. All right, let's see how you did. First of all, set up. The cube root, you'd make a third, and to bring it to the top of your fraction, you would have an exponent of negative 1/3. That is your most outside function, so that negative 1/3 would come out in front. Keep the inside the same. Subtract 1 from the exponent. Derivative of the inside. Well, derivative of 7 is 0. E to the negative 3x would be e to the negative 3x. But you have a negative 3x inside of e to the x, so you'd also have to do derivative of the inside again. with a -3. Derivative of the outside function, keep the inside the same, multiplied by the derivative of the inside function. Now we're going to start combining our product rules, quotient rules, chain rules, all of our shortcuts together. And what we have to start to recognize is which rules do we have and how should we apply it. So first of all, as far as setup goes for this one, I changed that square root to a half. Then I analyze my question. Do I have product rules? Do I have chain rules? Do I have quotient rules? Well, it doesn't look like I have a quotient rule because I don't have a fraction at all. How do you know if you have a product rule? You know you have a product rule if you can put a dot for times. I can put a dot there because that means times between those two things. And when you put the dot for times, the first one, wow, I didn't want that color. I wanted yellow. The first one, does it have a derivative? Yes. Sometimes you can put a dot for times, but the number out front is a 2. Then you're not going to use the product rule because 2, its derivative is 0. You don't need to do a product rule if you just have a number out in front. But anytime you have something with an x in both parts, right? The yellow part and the green part is the 2 multiplied parts. There's x's in both of them. Both of them would have derivatives. This is a product rule. Then in the product rule, can you see in the green part, we have a chain rule. We have something inside of the half. So we're going to have to do the chain rule if we ever have to do the derivative of the green part. So I see the product rule, and I say to myself, what are my rules for the product rule? For the product rule, I keep the first one the same, multiply by the derivative of the second. And what do I have to do for the derivative of the second one? It's a chain rule. So the half has to come out the front, keep the inside the same, multiply by the derivative of the inside. I'm still in my product rule. My product rule says now keep the second one the same and multiply by the derivative of the first one. So I'm going to write down what we were saying as we were doing it. Product rule was keep the first the same, derivative of second, keep the second the same, that's my product rule in purple. But while I was doing my product rule, when I got to the derivative of the second, it made me think of a chain rule, which has 2 parts, right? This part of the chain rule is the derivative of the outside, where I keep the inside the same. I'll put a black arrow there. And that part is the derivative of the inside. Where do derivatives play tricks in your mind? The purple, the orange, and the black are our shortcuts. Do you see that there's a lot of shortcut stuff going on? It's easy for your brain to be like, I'm working on one shortcut while I was in the middle of another shortcut and I forgot where I was in my shortcuts and I'm like confused. Can you see that happening? So we have to have a really firm grasp of the shortcuts in their wording, and then we have to remember where we were. So this is my product rule. But while I was doing my product rule, keep the first the same, I was like, I've got this. Things are good, right? That's like little thinking whatsoever, keep the first the same. Then when I got into the derivative of the second, it put me into a chain rule. And you do your chain rule, and sometimes when you get done doing your chain rule, you're like, where was I at? You might have to start your thinking over again and say, okay, where was I at? Oh yeah, I kept the first the same. Oh, now I've done the derivative of the second. So now I have to keep the second the same, derivative of the first. You might have to start yourself over again because doing the derivative part might get you lost. And then you have to take a step back and say, where was I trying to start? I was trying to do a product rule. Keep the first the same. Oh, now I've done the derivative of the second with the chain rule. Where would I have to go next? Keep the second the same, derivative of the first. Okay, so preliminaries. I'm just putting an arrow here that I would write that square root as 5x to the half. What do we have here? Do you see a quotient rule? You use the quotient rule when you have a fraction and something in the top has its derivative and something in the bottom has its derivative. If the top is just a number, we usually just use negative exponent rules to move things up. Okay, but in this case, it is a quotient rule. In the quotient rule, you have a top and a bottom. Here's the top, here's the bottom, here's the top. What do we keep the same? We keep the bottom the same, derivative of the top, keep the top the same, derivative of the bottom, over the bottom squared. So as far as the setup for this, okay, maybe you want to do these three parts first, because they are super easy. Why are they super easy? Because they're the things that stay the same. Keep the bottom the same there, keep the top, keep the bottom the same there, keep the top the same there, and the bottom squared here. So I keep the bottom the same. Then I have to do the derivative of the top. Do you see that the derivative of the top is a chain rule? There's a 5x inside an exponent of a half. So how do we do that? We bring the half out in front, keep the inside the same, subtract 1 from the exponent, then multiply by the derivative of the inside. Minus, keep the top the same. Do you see that the bottom is also a chain rule? You have a 1 minus 8x squared inside of a cube. So we would do the cube part first, keep the inside the same, then we have to multiply by the derivative of the inside. And this one I will show you the simplified version here. Because, and I'll highlight it with an orange box here, I want you to see that in the top they have a factor that's the same in the first term and the last term, which matches up with the factors that are the same on the bottom. Can you see that you could cancel out a 1 minus 8x squared all squared from all of them? That would leave me with 1 minus 8x squared in the first one, because 2 of them got canceled out. They're all gone in the second term because they both got canceled out. And you'd be left with only 4 of them on the bottom. Quotient rule often has, especially if you have some sort of power in your denominator, it's very likely that you'll have a common factor that can be simplified. I like to look for my product and quotient rules first. Could I put a dot for multiplication here where what's on the left has an x and what's on the right has an x? Absolutely. Can you see that if I put a multiplication dot right here, then this being my first one definitely has a derivative, and this being my second one definitely has a derivative. And that second one, with the cube root, you could do it like this, or you could make it to the third right away, and then 1 to the third is just 1, and x to the third would be on the bottom, which I probably would change to x to the negative 1/3 as the most nicest way to do a derivative. So I rewrite that equation as a result, and I still have a product rule, right? Because my multiplication is right there. Here's my second one, simplified. Here's my first one. So what do we do in a product rule? Keep the first the same, multiply by the derivative of the second. Then keep the second the same, multiply by the derivative of the first. So keeping part the same, like calculus is mentally challenging, so it's like they knew it was going to be mentally challenging, they built in breaks for you. Oh, keep something the same. That's easy. Now I have to do the derivative of the second one. Well, the derivative of the second one, now that I've done all that math to change it to x to the minus 1/3, is easy. Minus 1/3 comes out in front. Subtract 1 from the exponent. You guys are probably getting really good at subtracting by 1 by now. Then we keep the second one the same. And we have to do the derivative of the first one. And when we look at the highlighted yellow part, do you see that the first one is a chain rule? You have something inside of the 4. Can you remember yesterday when I said that the first method we did sucked? Right? Can you imagine doing all that dy dx off to the side? You don't have time to do extra work off to the side. It's too complicated already. We just need to do it smoothly. So in this case, the derivative of the outside, put the 4 out in front. Subtract 1 from the exponent. Keep the inside the same. And then multiply by the derivative. When marking student work in questions like this, the number one mistake that I see is students being too excited to do derivatives too quick. The keeping the same part is usually what causes the errors. It's like you have to keep it the same before you move on, but you want to do the derivative so fast that sometimes you do forget the part that stays the same. All right, let's do one more and then you can work on your take-home quizzes. And this one has a second derivative. So we have to find our first derivative. You see that your first derivative is a chain rule. You see that there's no product rule here. Or, I guess if you wanted to, you could rewrite x squared minus 3x times x squared minus 3x times x squared minus 3x and do a double product rule instead. Or you can multiply it out using Pascal's triangle. Actually, multiplying it out with Pascal's triangle seems a little bit of a struggle at the beginning, but it would make finding the second derivative really easy after the first derivative. But we'll do this as if you noticed the chain rule first. So all of the shortcuts, often you can do them in different ways, and you have that choice. If you see chain rule first, then you would say, I can do the derivative by doing my outside function is the exponent, so I bring the 3 out in front. Keep the inside the same, subtract 1 from the exponent. Multiplied by the derivative of the inside. I could take the 3 and distribute it with the blue and get 6x minus 9 if I wanted to. I wouldn't have to do that. But now when I look at it, I have a multiplication. This is my second one. This is my first one. So then I would have a product rule when I do the second one. What does the product rule look like? Well, I keep one the same. Keep that the same. Multiply by the derivative of the second one, which is a chain rule. The 2 would come out in front. Subtract 1 from the exponent would be a 1. Keep the inside the same. Then multiply by the derivative of the inside. Product rule, now we have to keep the second one the same. So here I keep the second one the same and multiply by the derivative of the first one. Just for fun, I'm using Pascal's triangle and I'm multiplying that out. If I did that, I would have got y equals x to the 6 minus 9 x squared x to the 5 plus 9 times 3, 27 x squared x to the 4, and finally minus 27 x cubed. The nice thing about using Pascal's triangle, 6x to the 5 minus 45x to the 4 plus 108x cubed minus 81x squared is my first derivative. And it just used the power rule. And then my second derivative, 30x to the 4 minus 180x cubed plus 324x squared minus 162x. My second derivative was relatively easy. My third derivative would be not hard from here either, because it's, if you just have the power rule, then the next derivatives are easy. If we had to find the third derivative with this, we would have like a double product rule here and another chain rule there, it could get very complicated quite quickly. Doable though. You just have to remember where you are in your shortcuts. So you have options. You can choose to simplify. You can choose to use your rules. I would say most students and most people, they just go and look, what do I have? And use the chain rule a lot. Seems like expanding it completely seems like, oh, that seems like more work. Even though in this one, if we kept going with further higher level derivatives, expanding it out is actually quite nice. Feel free to move around.